Application of Boyle's law to gas trapped in a cylindrical tube by a column of mercury. The gas is somewhere here. Then this red line, this red place is your mercury. The red is standing representing your mercury. So the mercury is trapping the gas down here. This is a cylindrical tube. Okay. So we have three cases. Look at this first case. Okay. You assume that we assume that the gas is somewhere here. Here could be dry air, could be whatever gas. So the tube, the capillary tube, it could be a capillary tube or what we call a cylindrical tube, is vertically open at the top. It's open at the top. So you assume that atmospheric pressure will be pushing down on it, into it, okay? So and the gas will be pushing up. The pressure of this gas, gas that we say is trapped, this trapped gas, could be dry air, could be some other gas that is somewhere, that is here, is trapped here by this mercury column. The value of the pressure of this, P stands for pressure, so the pressure of the gas will be equals to that atmospheric pressure, which you are representing by PA, plus this mercury column, the pressure due to this mercury column. Okay, so pressure of the gas equals to PA. You assume that atmospheric pressure will be acting downwards, maybe due to gravity and stuff like that. All right, so let's look at the second case. So if the atmospheric pressure, which is acting upward, is able to hold the column, both the mercury column and the trapped gas, it must be that this atmospheric pressure is larger. So the atmospheric pressure must be larger than the pressure of the gas, okay, the trapped gas, plus this length, this mercury column. See, this our mercury column here, this height, okay, x, and then the height of the trapped gas taken to be y2. So the expression is atmospheric pressure is equals to the sum of the pressure here and the mercury column. Now for the third case where you have the cylindrical tube in a horizontal position. Okay, so first case, vertical position, open at the top. Second case, vertical position, open at the bottom. While the third case, horizontal position. Now gravity is not really working here, so the atmospheric pressure is basically equal to the pressure exerted by the trapped gas. So take that the trapped gas should be equal to more or less the atmospheric pressure. You could be asked to find the pressure of the gas, pressure of the trapped gas. Okay, I said that the trapped gas could be, an example could be dry air, AIR. Okay, so the pressure of the gas can be obtained for all three cases. Now the three cases are depending on how the tube is oriented. Is it upside down, okay, or right side up, or horizontally? Now you might be asking, where did I get this expression from? Remember, Boyle's law says P1 V1 is constant, so it's equals to P2 V2 is equals to P3 V3. So the pressure of the gas across these three cases, the product of pressure and volume should be constant. That's Boyle's law for you. Okay, so this volume is gotten from, remember, volume is area times length. Okay, so if we look at the cross-sectional area of the tube, okay, we take it that the cross-sectional area of the tube is constant. We assume that the tube is the same tube is used. Okay, so it has a uniform cross-sectional area. So it's just the length that varies with the volume of gas. Okay, so as I was saying, the volume of the gas, this V that we have in this expression, can be reduced to, remember, volume is area times length, or length times length times length. So length times breadth, that's area times length. Now the area is taken to be the cross-sectional area of the tube, okay, times the length of the column. So this, if the area of the tube is kept constant, you can see the tube, assuming that it's the same cross-sectional area of the tube, okay, it has that same cross-sectional area, it's a cylinder, okay. So if it's kept constant, we can just say the volume of the gas is directly proportional to the length of the gas column. Okay, the length of the gas column, it's the length of the gas of this trapped gas. Okay, the length is y1 in the first case. In this case, it's y2. Okay, all this from here to here. Okay, that's length y2, and then horizontal. In this horizontal third case, it is length y3. Okay, so that's why we have the volume is being reduced to y1. Okay, because volume is directly proportional to the length of the gas column. cross-sectional area being constant. So PA, the first case is the case 1, the second case, and the third case. Guys, let's go. So this example we are looking at right now, we have it said a tube of uniform cross-section, okay, is closed at one end, contains some dry air. So this is our trapped gas, which is sealed or trapped by a thread of mercury 15.5 centimeters long. Okay, when the tube is held vertically with the closed end at the bottom, the air column is 22 centimeters long. Okay, I'm using my own I want to use this explanation. So the tube held vertically with the closed end at the bottom. So over here you have your trapped, okay, the trapped gas down here. Okay, so it says that the tube is held vertically with the closed end at the bottom. The air column is 22 centimeters long. The air column, okay, that's the trapped air, has a length Y1 of 22 centimeters. Remember, this is the mercury column. X is given as 15.5 centimeters. But when it is held horizontally, I'm here. But when it is held horizontally, that's the tube. The air column, that's the dried air or the trapped dry air. The air column is now 26.4 centimeters long. So I'll show you what that looks like. So when the tube is held horizontally, so this is horizontal, okay, the trapped air over here, let me just show, no, trapped air, it is trapped by the mercury column. The length changes to 26.4 centimeters. Now remember, the length of the mercury column does not change, it remains 15.5 in both cases. Okay, so we're going to use case 1, what I call case 1, and case 3. You can call it case 1 and case 3, okay, just for convenience, so that we can know that the first case, you can see that the first case, you have to admit that the weight of atmospheric pressure is going to be held, it's going to be heavier. So PG is holding up, okay, it's like holding up both the weight, atmospheric pressure PA, and the pressure due to the mercury column. So PA plus X will be equal to PG. So PG is greater than PA. PA plus X, this is the expression for the pressure of the dried gas or trapped gas times the length, okay, the length of the trapped gas, Y1. So it's standing for V. Remember I told you that volume is directly proportional to the length of the trapped gas. Taking that A is constant, cross-sectional area is constant, okay? So this volume is being represented by Y1. So Y1 is the length of the trapped gas. So in the second case, is equals to the second case. Remember, PA is equals to PG directly, okay? For the third case, in the horizontal position, P is equals to PG directly. So this V is being replaced by proportional to this length. Alright, enough said. So PA plus X. Our X in the first case is 15.5. That's the length of the air, the length of the mercury column. Okay, it's the mercury that is trapping the air here. Okay, so the length of the mercury column X. Okay, so put that in expression. You have Y1 is 22.0 if you like. So Y1 is 22 equals to PA times 26.4. Y3 is 26.4 in this position. So expand your bracket, 22 multiplies everything in here, and then you have that. Collect like terms, and you have 4.4. So atmospheric pressure is basically 7.5.